Hi everyone. Here you are going to learn about the convolutional encoding. Okay, convolutional encoding means you are trying to encode the information bit. Okay, or you are trying to convert that information bit into an code word, or in other words, you are trying to find the output code word. That is, you are trying to find the value of v from the information sequence or from the input, that is u. So here convolutional encoding means you are trying to find the value of v when u is given. That is the meaning of convolutional encoding. Alright, so convolutional encoding has two approaches. One approach is called as the time-based approach, and the other approach is called as the transform domain approach. So here we will you'll be using time-based approach. Okay, so see, in my last video, you all will be wondering right now, in my last video, that's exactly what I did, right? In the last video, what I did was that I used a 212 convolutional encoder, and then I applied an information sequence into the convolutional encoder, and then I found the output value, right? But that process is actually a very long process. In that case, that you have to always sit and find out the values of every shift registers, what are the values that is coming out of it, and then from there you have to find then for every shifting values you need to compute, or you need to calculate the value of the output, and then finally you have to combine the output and then write the answer. So that process is actually very tedious, right? Then you have to draw the circuit, and then you have to look what is the value of every shift register. So that's what we did in the last video, but that is actually kind of a more time consuming process. What is much more better is you apply any one of these approaches. That is, either you apply the time-based approach or you apply the transform domain approach. So in that case, you will get the value of the output really quickly. Okay, so in order to demonstrate that, the best way to understand this approach is by using an example. Okay, and in my first example, I'm going to use a 213 convolutional encoder. Okay, so now I want you all to read this question. Construct a 213 convolutional encoder whose generator sequences are given by g of 1 is equal to 1011 and g of 2 is equal to 111. And then now they're asking, also find its output when the information sequence is 10111. So here this is the input, right? And they're asking us to find the output v. Okay, and this approach, so then that is, you are trying to find the output value, and this approach we are going to use is the time-based approach. Okay, so first let me draw the circuit, right? So before drawing the circuit, let me first write the generator sequence. What is the value g of 1? G of 1, I use a different color pen just so that you will understand how I'm doing this. 1 0 1 1. Okay, this is g of 1, and what is the value g of 2? Let me use another color. G of 2 is equal to 1 1 1 1. Okay, I'm using green for g of 1 and orange for g of 2, just so you don't have to use different colors when you're writing for the time of exam. This is just for your own understanding. Okay, so now what I'm going to do is I'm going to draw the encoder. All right, okay, I'm not going to use 212 and convolutional encoder like I used in the previous exam. That is too easy. Let's take it up a notch. Let's increase the difficulty. Here it is 213. So I have two generator sequences over here. So let's draw them. So first what I'm going to do is the value of n is equal to 2, the value of k is equal to 1, and the value of m is equal to 3, right? So I will draw the input first. Okay, let me draw the input. Only one input is there, right? So let me draw only one input, that is this input right here. And then what is the value of m? The value of m is equal to 3, which means for every input there are 3 register blocks or 3 memory blocks, right? So here the value of input is, the value of the input bit is 1, which means there's only one position. So therefore this position will have 3 blocks. So that is what the meaning of, that is the meaning of m. That is for per input, right? The number of register blocks per input. So since there is already one input, so there will be only 3 shift register blocks. Let me draw the 3 blocks. This is the 3 shift register blocks. Okay, that's it. Okay, this is it. That's it, right? This is the 3. So I drew 1 and this is 3. register blocks. If there were 2 input, right, so I just simply assume if it was 2, 2, 3, then there will be 2 input. If it was 2 input, then you have to draw 1 input with 3 blocks and another input with also with 3 blocks. Okay, just so for your understanding. All right. So now next is I'm going to look at the value of n, or the number of the output. What is the number of the output bits? The value of n is equal to 2, which means there are 2 outputs, right? Let me draw those 2 outputs. How to draw it? I'll draw it like this. This is one and this is the other one right here. Okay, so this is u. Okay, this is u, and this is called as v of 1 and this is called as v of 2. Okay, and you have a switch or a 2:1 multiplexer, whatever you want to call it, and this is called as v. This output is called as v, that is combined. This is a switch. Okay, it combines both the output values and then it comes out through this switch over here. And since there are 2 outputs, there will always be 2 XOR function. One XOR function for this fellow and the other XOR function is for this fellow right here. There you go. Okay, hope you draw more neatly than I do. Right, so here what I'm going to do is I'm going to now look at the, next step is I'm going to look at the generator sequences and I'm going to draw the corresponding connections, right? So here the connection is, I'll use green pen for that, for G of 1. So here G of 1 is 1 0 1 1. So 1 0 means no connection, 1 and 1. This is called as 1 0 1 1, right? 1 0 1 1. Okay, next is G of 2. G of 2 is 1 1 1 1. So G of 2, I use orange pen. G of 2 is this one, 1, that's this one, 1, that is this one over here, this connection, which means this one and this one, and this is called as, this is how you construct a 213 convolutional encoder. Okay, so here you have the information sequence and here you get the output. Okay, so this is the example that I'm going to use to explain what is time-based approach. Okay, I'm going to explain the time-based approach using this circuit as my example, right? But I am not going to explain to you the working of the circuit. I already did that in the last video. Okay, and that is, like I said before, that is actually a time-consuming process, right, in order to find the output. But here I'm going to use this, I'm going to find the value of the output. Okay, I'm going to find the value of v, which means to find the value of v means I have to find the value of v of 1 and v of 2 simultaneously, right? Because for every bit that enters the circuit, since the value of the input is equal to 1, every 1 bit will enter the circuit, and once when 1 bit enters the circuit, 2 output bits will be generated simultaneously, right? So we need to find the value of these 2 output bits that has been generated, right? So here I'm going to use time-based approach, and they have already given the information sequence. What is the information sequence? 1 0 1 1 1, which means I am going to input right here 1 0 1 1 1. What it means is that this 1 will first enter the circuit, then this 0 will then enter the circuit, then this 1 will enter the circuit, then this 1, and after that this 1. Okay, after when all this information sequence enters a circuit, you need to add 3 more zeros. Why 3 more zeros? Because the value of these shift register blocks is equal to 3, right? The number of shift register blocks is equal to 3, and you need to flush out those answers also. So that's why along with this information sequence, you apply 3 more zeros, or you input, or you give 3 more zeros into the circuit, right? Now, oh yes, and one more thing also I want to tell you about. Okay, one interesting thing. Okay, see, other than looking at the circuit, is it possible that we get these values itself at the output? Is it possible that v of 1 is equal to g of 1 and v of 2 is equal to g of 2? Is there any value where you give the input such a way that you will get the same values at the output. Is it possible? Yes. The answer is yes, it is possible. And how to do that is, all you need to do is apply a single 1 into the information sequence. See, suppose if I give, what I meant is, if u is equal to, okay, if u is equal to 1, 0, 0, 0. If the value of the input is 1, 0, 0, 0, then definitely you will get these same values over here. That means you will get v of 1, you will get the answer as 1011, and v of 2 you will get 111 if the information sequence is 100. That is, all you have to do is simply apply a single 1 bit. Okay. Why these 3 zeros are being applied? Because, like I told you before, there are 3 shift register blocks and you need to flush out the answer. So that is why after applying the input bit, you need to clean out the answer, or you need to extract the remaining answers from the shift register. So what do? You have nothing else to apply. You have no other information to apply. So you apply 3 more zeros. Okay, that is what you're going to do over here. So you see how this works is, you see, I think if you really understood this, right, if you really enjoy this, you'll understand. You have already learned in your signals and systems class that there is something called as the impulse response. What is the impulse response? Impulse response means, an impulse signal means you are applying an infinite amplitude at t is equal to 0, and for the remaining time values, the value of the signal is equal to 0, but only at time t is equal to 0 the amplitude is infinite, or the energy of the signal is unity. If it's a unit impulse signal, the energy of the signal is unity at t is equal to 0, and it is 0 for the remaining values of t. That is called as the unit impulse function, right? If you're talking about digital impulse, if it is a digital impulse, then you will be applying a unit amplitude at time t is equal to 0. That's this one over here, the unit amplitude. And that is how you understand the impulse response. By simply applying an impulse at the input of a system, you will be able to get the impulse response. And that is exactly what you see here. These generator sequences are nothing but the impulse responses of the output of the circuit when the input is a single impulse. That is, if you simply apply a 1 bit and the remaining 0, these remaining zeros you are applying in order to flush out the answer, you will get the same values at your generator sequence. Okay, that's it. Okay, enough of story. Now let us apply the time-based approach right here. So a time-based approach means nothing. It's very simple. All you have to do is, it's very easy. Okay, this is it. V of 1. If you want to find the value, what you're trying to do is you're trying to find the value of V of 1 and V of 2, and then you try to combine them to find the value of V. So what is the value of V of 1? V of 1, very simple. V of 1 is equal to U into G of 1. That's it. V of 2 is equal to U into G of 2. That's it. This is called as the time-based approach. See, very simple, right? This is all you have to do is simply take the information sequence, multiply with G of 1, you will get V of 1. Take the information sequence and multiply with G of 2, you will get V of 2. And then finally you combine the answer. This is called as time-based approach. That's it. Finished. So let's do this, right? So let's do this quickly. So here V of 1, right? So I want to find the value of V of 1 is equal to, what is the value of U? 10111. So I will take 10111 into, what is G of 1? G of 1 is 1011. 1011. Oh my god, I hope I'll get the correct answer. 1011. Okay. So I'm going to need to multiply both of them to find the value of V of 1. Let me multiply them. 10111 into 1011. What will I get? Multiply with everything, I will get 10111, and here again I will get 10111, and then here it will be 0, so everything will be 0 right here. 0 0 0 0 0. How many zeros? 5 zeros, right? Yeah, 5 zeros. Then you have 1 again, 1, so I will multiply this with 11101, right? And what you do is you simply add all of them, you will get 1 plus 1 is 0, 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 0 plus 0 is 0, and here it is 1. Okay, when I'm adding this thing, don't think that this is binary addition. This is not binary addition, this is XOR function. Okay, modular 2 addition. Right, this is not a half adder or full adder or anything like that, right? This is not that kind of a thing. This is actually just you are applying a modular 2 addition or XOR function, that's all. So when I'm saying 1 plus 1, what I meant is 1 XOR 1. XOR is also called as a modular 2 adder. So 1 plus 1 means what I meant is 1 XOR 1. Okay, so I will get this value. So this is the value of V of 1. It is 1 0. How many zeros? 1 2 3 4 5 6. 0 0 0 0 1 2 3 4 5 0 1. So this is the value of V of 1. Next I'm going to do is I'm going to find the value of V of 2. So to find the value of V of 2, I think now you can, if you want, you can do this along with me, right? So you don't have to waste your time. What is the value of U? U is 1 0 1 1 1. And what is the value of V of G of 2? Value of G of 2 is 1 1 1 1. My goodness. So when I'm multiplying these two, I will get, let me multiply them, 1 0 1 1 1 into 1 1 1 1, and I will get, I have to write this thing 4 times. 1 0 1 1 1 1 0 1 1 1 1 0 1 1 1 1 0 1 1 1, and then I have to sit and add all of them. 1 0 3 ones, that is 1, 3 ones, that is 1, 1 plus 0 plus 1 plus 1 is 1, 1 plus 1 is 0, 1 1. There you go. So this is the output value. That is V of 2 is 1 1 0 3 ones, 1 1 1 0 1 0 1. So this is the value of V of 1. This is the value of V of 2. So what is the value of V? The value of V is nothing but simply combine these two answers, right? That is, you see, what is the first bit over here? 1. What is the first bit over here? 1, comma. What is the second bit over here? 0. What is the second bit over here? 1, comma. So this is the first output. See, the first output is 1 1. The second output is 0 1. What is the third bit over here? 0. And what is the third bit over here? It's also 0. What is the fourth bit over here? Is 0. And the fourth bit over here is 1. Okay, don't make mistake, right? And what is the first bit over here? 0. And what is over here is 1. And what over here is 0. And here it is 1. And here it is 0. Here it is 0. And the last output is, the last bit over here is 1. And the last bit over here is 1. So this is your output. Okay, this is called as time-based approach. Okay, that is, you are multiplying the corresponding value of the information sequence with the generated sequences. Okay, that is it. This is called, so this is the output you get. How many output you got? 1 2 3 4 5 6 7 8. You got 8 output values, right? You got 8 output values when you applied a 5-bit information sequence. When the number of the information sequence is equal to 5, you got a 8 output. How did you get that extra 3? Where did you get that extra 3? You got the extra 3 because after applying the information sequence, right? After applying the information sequence, you also apply 3 zeros along with it. Like I said before, you apply the 3 zeros along with it in order to flush out or in order to extract the remaining answers. That is why you got 8 answers or 8 output values. So this is your output. Okay, this is called as time-based approach. Now, another thing about this time-based approach is that you can actually you find the value of the time-based approach by using this equation, this matrix equation. You already know this equation. Right, this matrix equation, you have already seen this equation when you are learning about the NK linear block code, right? Where V is the output matrix, V is the output matrix, output matrix or this value or right here. U is your information sequence or this matrix right here, and G is called as the generator matrix. So if you're going to apply this method, that is V is equal to U into G, then what you need to do is you need to find the value of G. You need to find the value of the generator matrix. So what is the generator matrix of the 213 convolutional encoder? How do you express the generator matrix of a 213 convolutional encoder? For that thing, to understand that, what you need to do is I'm going to first construct the generator sequence or the generator matrix. So how to construct is, you need to understand that first and foremost, you need to understand that the generator matrix has capital letter L rows. The generator matrix has capital letter L rows. Okay, L rows, where L is the length of the information sequence. L is the length of the information sequence. So here in this example, the value of L is equal to 5 because there are 5 bits. The information sequence has 5 bits. So the value of L is equal to 5. Okay. And next will be the number of columns, and the number of columns will be, hope you will try to understand, n into m plus l. N into m plus l. Okay, why n into m plus l? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. That is, the number of columns will be 16. How did 16 come? You got the 16 because 2 into 3 plus 5. This is how you got 16 columns. Okay, this is, I hope you will try to understand this by yourself. It will be always a very good, interesting experience if you try to understand all this by yourself, right? See, how did you get, why it is n into m plus l? Because totally you will get, how many output values you will get? You will get m plus l output values, or 8. You will get 8 output values, right? How did you get 8 output values? Because along with the information sequence, you will apply 3, along with your information sequence, you will apply 3 more zeros in order to flush out the remaining answers, right? And then what you do is that you combine both of them, right? Because at a single time, you will get 2 bits. At a single time, you will get 2 answers. First, you will get 1, 1, then you will get 0, 1, then you will get 0, 0, and so on. So like that, how many times you will get the output values? You will get 3 plus 5, or 3 plus 5 means 8 output values you will get. 8 output values or 8 branch words, right? 8 branch words. You call it as 8 branch words. Here it is m plus l branch words. Okay, branch words, or you can also say, this can also be written as m plus l branch columns, columns, branch columns. Okay, you will get m plus l branch columns or n into m plus l columns. Why? Because each branch word is equal to 2. Each branch word is equal to n. Here you see if the value of n is equal to 2, which means every single output value has 2 bits. So those 2 bits are these bits, that is 1 1 0 1 0. So that's single time. First time you will get 1 1, second time you will get 0 1, third time you will get 0 0, and so on. So therefore you will get n into m plus l columns or m plus l branch columns, where each branch is consisting of 2 bits, right? So this is how we say it, right? All right, so this is how we say it. So here I'm going to use an example. So here the value of G is equal to, so I'm going to now combine the value of G. So what is the value of G over here? How to write? Let me again, I'm going to write my G of 1 value. What is the value of G of 1? G of 1 is equal to 1 0 1 1 The value of g of 2 is equal to 1 comma 1 comma 1 comma 1, right? So now see how I'm going to write the answer. Okay, I'm going to 5 rows, 1 2 3 4 5. Okay, 5 rows, and the first I will get is 1 1 0 1 1 1 1 1. See, look over here. 1 1 0 1 1 1 1 1. I combined the generator sequence, right? I combined the generator sequence. That is like this. I made the generator sequence like this. That is 1 1 0 1 1 1 1 1. Okay, I combined the generator sequence. So this is 1. The second row will be 1 1 0 1 1 1 1 1. Okay, what I did is I shifted this by a single branch word. The second row I shifted it by a single branch word. Okay, one branch word has 2 bits because here the value of n is equal to 2. Now this third row I'm going to shift it, so it will become 1 1 over here, 0 1 1 1 1 1. The fourth row I'm going to shift it, so it becomes 1 1 0 1 1 1 1 1. The next time again I'm going to shift it, 1 1 0 1 1 1 1 1. That's it. This is the matrix. Okay, the blank space over here is nothing but zeros. Nothing but zeros. Simply fill them with zeros. Okay. This is the generator matrix. This is how you construct the generator matrix. Okay, and I know some of you will be confused. You will think, what kind of a generator matrix is this? Okay, this is actually a stupid generator matrix, because here the number of rows of the generator matrix depends on the length of your information sequence. So what if the length of information sequence is 3, or what if your length of the information sequence is 7? Okay, and what you thought is actually correct. The generator matrix depends on the length of the information sequence. It is just that you need to accept that reality. There's nothing new about it. There's nothing special about it. The length of the information, the number of rows of the generator matrix depends on the length of the information sequence. So what you thought is also correct. So you might be thinking, in that case, the generator matrix always changes. In that case, the generator matrix always changes, because the next time when you are going to apply the next information sequence, and if that information sequence is not equal to 5, then the number of rows of the generator matrix will also change. And what you thought is actually correct. It's actually correct. The generator matrix changes with respect to the length of the information sequence. It changes. Okay. So this is actually, so what I'm trying to tell you is that this generator matrix it's only used, or it's only applicable for this particular information sequence, or when the length of the information sequence is equal to 5. If the length of the information sequence is equal to 6, then what you need to do is you need to draw another row downwards, and you need to shift this generator sequence, this combined generator sequence, by another branch word, and then you write the answer. And the remaining space, blank space that you see anywhere, you simply put zeros over there. This is how you apply. Okay, and when you multiply V is equal to U into G, where U is 10111. U is 10111 and G is his generator matrix. Okay, I want you all to do this for homework. You multiply U with this value, this 1011, with this generator matrix, and I assure you, you will get this very same values. You will get the same values right here. 11010010010101010011. You will get that same value. Okay, so this is the time based approach of a 213 convolutional encoder. Okay.